this is a great crowd. This is really good. The more people, the better. I love it that way. More interactions. Feel free to ask me questions as I go through this. I want you to get two things out of this talk. Okay? If you don't remember anything else, two things. One is, it is a fabulous time to be alive and have a curious mind and be great at solving problems. There are so many problems available now, in a positive way. There's so many problems in the world today that are just waiting for people to solve them. And I'm almost envious of the younger people now who are on this brink of being able to solve these problems. And it would be ecstatic if there's some people in this audience, young people, who could solve some of these great problems that are confronting the world today. So that's the first thing. Great time to be alive, to solve problems, and help the world. And second of all, math is fun. Okay? Sometimes people think math is just like, adding numbers and all that. I want you to get the image here. Math is a lot bigger world than you think it probably is. My research I do, when I talk to a lot of people, is math and soap bubbles. And I study the math of soap films. That's a totally different talk, but it gets in kind of that image. Careers in STEM fields or math. STEM means science, technology, engineering, and math. There are a lot of good career opportunities. In fact, fantastic career opportunities. Whether you want to, I have one daughter, my fourth daughter, who's at the university right now. She wants to go into sports analytics. So using math, computer, statistics to help sports teams do better. She would love to be a sports analytic person for a soccer team. So I think that would be really cool. My oldest daughter has a job with Raytheon, which is an engineering firm. She has a master's degree in math, has this job. Raytheon is a company that's working on, among other things, the Iron Man suit. If you've seen the movie Iron Man, there are people trying to create an Iron Man suit. Not one where you put a nuclear device in somebody's chest. There's some ethical issues about that. But creating a suit where you can run faster, lift things more, and do things like that. So, great time to be alive, solve world problems, and math is just a big open world with lots of wonderful things going on. Okay, so we're going to talk about movies. What are the highest grossing films? What do you guys think? So kind of neat, because the crowd's a little bit loud. Raise your hand if you got one. Yes?
Gone with the Wind.
Gone with the Wind. Okay. Gone with the Wind.
Jurassic Park.
Jurassic Park.
Avatar.
Avatar.
Grand Budapest Hotel.
Frozen.
Frozen.
Oh, yeah.
What was that?
I agree with that.
Oh, you did Frozen. Okay.
Star Wars.
Star Wars. You're getting some of them. All right, let me show you the list. Here's the top 20 as of the end of last year. So, Avatar, number 1. Okay, Titanic, Avengers, Harry Potter. 5 was Frozen. Frozen may have moved up a little bit. But I think it pretty much did its run there. Unfortunately, Gone with the Wind. But these are not adjusted for inflation. I mean, these were the amount of money they earned. So, $1 back then is not the same as $1 nowadays. Okay. Now, all these movies, except for one, have something in common. Okay. The last one here, Lion King, has one thing that's different than all the other movies. And that is math was used in the first 19 movies, in making the first 19 movies, but not in The Lion King. And math is used in the computer graphics imaging of all these movies, the CGI. Lion King was the last animated movie that everything was drawn by hand. Okay. If you remember when Lion King came out, that maybe shows how time is changing. I remember Lion King taking my daughters to go see Lion King. All right. So why is math involved in movies. Because, usually you don't, like, they had the Oscars, okay, Academy Awards last weekend. You didn't probably hear a lot about math. Those people were standing up giving their acceptance speeches. How's math used? Well, a few years ago, I ran a session there's an annual math conference, largest math conference in the world done annually, and I worked with a guy named Tony DeRosa at Pixar, and we organized a session on Hollywood movies and mathematics. And one of the people we invited was Rasmus here. He's a senior research scientist at Disney. Now, this is one thing that's going to be maybe a little bit new to a lot of people. You may not think that Disney or may not realize that Disney and Pixar have research groups in making their movies. These are people with PhDs in math, science, computer science, and they work on problems just like a research professor would work on at the university, but their problems are geared toward making movies better, using math, science, technology to do that. Okay, that's what he does. And this is their logo, the science behind the magic. And he said, movies model the real world, or at least they want them to model the real world. Okay? The real world is dictated by physics, and the math is the language of physics. So that's how he described why math is used in the movies. And so we're going to talk about some areas where math is used. The movement of animated characters, the simulation of physical objects, the light shading on characters, and the flowing and crashing of objects. And here are some examples of some movies we're going to talk about. And maybe you've seen some of these. All right. So we're going to start off with moving of animated characters. How are characters moved in the movies? Now, when I grew up, okay, so it was a while ago, when I grew up, some of you may remember this, they would take a piece of paper and they would draw a character on it, and then they would do another piece of paper, and it would be really similar, but just a little bit different. And they would do, like, you could do 100 sheets of these, and then, right, some of you are just doing this, you're going to, like, flip them and just see them move and all that. And that's the way people sometimes think of animated movies. And Lion King was like that. That's how they did Lion King. But they don't do that anymore. Okay. So, what do they do? Well, we're talking about an example from Star Wars with Yoda. Okay. How many people have seen Star Wars? Maybe I should phrase it. How many people have not seen Star Wars? Wow. They admit it too. Well, I mean, I guess it's kind of different. You know, the first three that came out were really good, and then there were the next three. So hopefully, the next one that comes out will regain. All right. So let's see. Movie Yoda. So in the Empire Strikes Back, the second movie that came out, Yoda was a puppet. Okay, so they're little puppets moving around. That was the first movie where you actually saw Yoda. All right. In later movies, Yoda was moved using animation and mathematics. And so here's some mathematics. If you're a math major, you might recognize some of these terms. They're classes they can do. And so here's a representation of Yoda. And what they did was they put these little grids on him. Headlines. All right. And you may remember, so in the second movie, when The Empire Strikes Back, they have Yoda, he kind of moves really slow, he's really old, and he passes away in that movie. If you go back then to, I don't remember which one it is, of the newer ones, they have a scene where he's like has the lightsaber, and he's like jumping up and down and doing all this stuff. Okay, you could not do that with a puppet. But you could do it with computer animation. Okay, so that's why they were able to do it. So let's talk about this. So just like you think back to geometry, you have this grid on them, and these form what we call polygons. And when two lines connect, we have a vertex. in this representation of Yoda, there are over 50,000 vertices where the lines meet, and these form polygonal regions. What you need in the computer to represent each of these is the location of each vertex, okay, and that vertex will be in 3 dimensions. And then the vertices that determine each polygon. So in doing that, we can move that representation of Yoda by using a thing called matrix multiplication. And you may remember, okay, these matrices are these big things with lots of numbers in them. All right. In this case, you can store the information about that representation of Yoda with a matrix that's 50,000 by 3 matrix. Now, 50,000, if I were trying to write that on the board, yeah, the talk would be over before I finish. Okay. You take that matrix and you multiply it by this smaller matrix, then it would rotate the character. And that would only require about 500,000 calculations. Now, hopefully this is not something that a math professor would give to somebody on a exam question, in class exam. It's going to take a while to do that. All right? So, this is, with that, 500,000 calculations, you can have Yoda going from here to here. All right? And this example was shared with me by Jim Chartier at Davidson College. So that was how they first started out. And actually, we just had the president of Disney come and, Ed Catmull, come and speak at BYU a few weeks ago. He was one of the, in Utah actually, in Salt Lake area, the University of Utah, they were one of the first places to do some of these animations by putting grids on characters. And some of those people left to work at Disney, just to help work at Disney. All right. Now here's Tony DeRose. He works at the research group at Pixar. He uses math to develop new techniques to move animated characters. And we're going to talk about the movie Incredibles. Now, how many people have seen the movie Incredibles? This is a pretty popular movie. How many people did not see Incredibles? Okay. All right. In this movie, there is this character right here. What is his name? Dash. Why is his name Dash? Okay, because he moves really fast. Now, if it would take 500,000 computation, to move, just to rotate a character, to make a character really move fast, would require lots and lots of calculations. Now, you may think, well, computers can do this. But at the time when this came out, they couldn't do it for an economical price. It would cost, the amount of computer time was really expensive. And so they couldn't make a movie, an animated movie, where the characters could really move that fast. So they had to come up with a new way to do that. And that's the problem that Tony DeRose worked on. So, here's a little clip. To remind you about the movie.
What's the toughest thing about being a superhero? Trying to live a normal life. Whether it's pumping up.
That's Dash.
Dinner with the family.
Okay. And being a father of 5 daughters, I can kind of relate with dinner time and sometimes being like that. Okay. So, here's the situation. Here you've got the character Dash with the grid on it. And the problem is you construct the grid on the character. You want to move the grid points using linear algebra. It requires a lot of calculations. What is the more efficient way to move animated characters? That was the problem that they came up with. Okay? So think about this for a moment. But while we do this, we're going to take a little commercial break. Okay? So, I happen to have some t-shirts here that I bought. And these t-shirts say, be creative. This is from a website we developed called weusemath.org that talks about how you can use math in different careers, and then there's a little inspirational thing about math being creative. So I brought some to give away. So I'm going to ask some questions here. The first one I'm going to give away is going to be for the youngest person in the audience. So, do we have anybody that's under 16? We got 1, 2, and 3. That's kind of, I can't see back there. That's like eating cookies. All right. How old are you? 11. 12.
15.
15. All right. You get a shirt. Unless you got to eat cookies. You want to have the cookies instead? You're thinking about it. What do you want?
You want the shirt?
Okay. Here you go. All right. Back to our regular program. All right. Now that you've had some time, did anyone come up with an answer to this problem? Pixar is hiring. Yeah, what did you think?
You don't have to move all of the pixels. You just have to pick out the ones that are the more important ones if he's moving quickly.
Ah, okay. So because he's moving quickly, you may not see the whole character?
Right, don't move all the detail.
Okay. All right, good idea.
Move them for their distances, so you have less resolution, but since he's moving fast, then it doesn't matter.
Ah, okay. Because again, using the idea of moving fast, then you don't have to do it in smaller increments, it's larger. Okay?
Maybe use combinatorics to generalize with fewer calculations.
Okay. That one would probably take a little bit more explanation, and I'm not going to go into that right now. Well, this is what they came up with. They developed a thing called a cage method. And what they do here is they take the character and they enclose them in a cage. Now, this cage, so it would be like, you might have like a box here around and a box around the body. And because of that, they can put fewer number of vertices on the cage. All right. And so the goal would be that instead of moving the arm, just to move the cage. And in doing that, so in this representation of Dash, they had 8,000 vertices. And on this one, for the cage, they only need to do a little more than 100. The difficulty, though, is just because you put a cage around the character, if you want to move the arm, if you move the cage, the arm doesn't move automatically. Okay? They had to develop the math so that when they move the cage, it would automatically move the arm in a realistic way. So just because you have a cage around them, you move the cage, the arm just stays there. But if you develop the math so that when you move the cage, the arm moves in a realistic way, then this would cut down the number of calculations, okay, from 8,000, where you have 8,000 vertices to about 100 vertices. It would cut down the computations a lot. All right. So how do you do that? Well, here's the math problem. Okay. Suppose you have these vertices, and you want to be able to move the vertices, just the vertices, but then have the interior points, all the interior points move in connection with that. All right? And how can you do that? It's a calculus problem. And basically it's this idea, you have, it's called the center of mass problem. So you have this representation for a vertex, this representation, this, and you have these different masses here. And you can find the coordinates, the center of mass, by using this formula. This 3 comes from this mass, and this -1 comes from this x-coordinate, this 4 from that mass, that 2 from there, and so forth. And then these are just the sum of the masses combined. You can do that for x and y. So that's what they did. Mathematically, it looks like this. All right? And I'm going to show you a video kind of representing that. So in this video, this will be presented by one of the research scientists from Pixar. He'll be talking. You'll notice that he doesn't quite sound like one of the actors in Hollywood. Sounds more like a professor. Okay. When they call this is the mean value coordinates, it's piecewise linear on the boundary, which if you don't know what that means, that's okay. It measures distance euclidely, and it works well for combinations.
We're going to start with a little example using mean value coordinates to deform an object shown in blue with a convex cage shown in black here. So when we begin, the cage points can be moved independently of the object points. Now what I'll do is bind the object points to the cage points, and as I move cage points around, you'll see the object deform smoothly.
So they use that mathematical approach from calculus to do this. And you may have saw at the very beginning, they did move some of the vertices, but they didn't move the interior points because they had to use the formula to do that. And then once they connected that, they did it all manually. But there was a problem with this, and this often happens when you try to solve problems in the world. Okay, your first attempt doesn't work. Okay, it doesn't mean that it's the end of the world. Okay, it just means you have to work on it some more. All right, and the problem was mean value coordinates don't work well for non-convex shape. Now, what's a non-convex shape? Well, a convex shape is a shape where you can connect two dots or 2 points in the shape, and as you connect them with a line, and that line stays within the shape. Now, if I take my legs here and I connect my kneecaps, that goes outside my body. That's a non-convex shape. Well, that's not very good for animated characters, because most animated characters have legs or arms. So this wasn't going to work. And this is shown in this.
In this next example, we're going to use mean value coordinates to deform an object bound to a non-convex cage, such as motivated by this bipedal character. As I move some of the points around, you'll see behavior very similar to that we saw a moment ago with the convex case. One problem arises if I move the points down here on the left leg, and you can see that as I move the points on the left leg, the object points on the right leg are moving a considerable amount, and they're counter-moving with the cage plates. It's highly undesirable in character animation.
Yeah, unless Brad Pitt was playing a scientist, I don't think he would say that's highly undesirable. Okay, because again, these are research scientists working for Pixar. So that was the problem. They tried to do it correctly this one way, it didn't work, so they come up with a new way. And so instead of doing these mean value coordinates, by the way, if you had calculus, you may have heard the term mean value before. You may have also heard harmonic coordinates. Okay, and they satisfy a certain math equation. If you're not familiar with that math equation, it's okay. You can still understand the topic. All right. These are similar to mean value coordinates, but they measure distance in the cage, which is what they want. All right. And so here's a video clip of that.
Harmonic coordinates extend to 3 dimensions, and in fact they extend to any higher dimension, as we showed in the paper. As a 3-dimensional example, I've got here a cage consisting of a triangular mesh in 3 dimensions, into which I've embedded an object. The object has about 8,000 points, and the cage has about 112 points. I've then harmonically bound the object to the cage and crudely articulated the cage. So if I pull the cage around in a very crude fashion, you'll notice how the object moves with a very smooth deformation. This example is all running in real time on a Macintosh G5 to give you a feeling for the speed of the system. I have all the local control behavior that I have in 2 dimensions, and so I avoid the artifacts and mean value coordinates in 3 dimensions. Recall that mean value coordinates measure Euclidean distances, whereas harmonic coordinates measure distances within cages. So as I move the left leg, you'll see that in the right leg, you'll see that the left leg is staying completely fixed.
So this is really kind of cool, I thought. They had to develop this math, and then they implemented the movie. Now, when you saw the movie, you never really thought about this. And so what they would do is they'd develop this old math, they'd write a program for it, and then the animators, who didn't have a math background, could then run the characters to do what they wanted to do, but maybe it would be allowed for them to do it really quickly because they have this cage method. I just think that's really fun. That would be fun to be working on problems like that. Okay, so next time you watch Incredibles, think about that a little bit. How did they do these types of things? All right. Crashing of objects. So this is Adam Sidwell. Works in Hollywood as a freelance person. He's worked on some of these movies, which have been popular. I won't necessarily say they're high-quality movies, but they're fun movies. Okay. And he uses math to develop techniques to simulate crashes in realistic ways. So when you see something crash in a movie, what you're doing on the computer is they're just getting closer and closer together, and then their coordinates overlap. But there's no crashing. They just overlap. But that would make a really dull movie. These things just flop, and you're like, wow, that was exciting. So how do you do those crashes? How do you represent those things? When I met Adam, he said, "Do you want to see my resume?" And I was kind of thinking, that's a weird question to ask him for a resume. I'm not hiring people for Hollywood movies, but I'm thinking, okay, you want to show me this piece of paper that says, movies you worked on and all that. Instead, he showed me this, which is part of his resume. Okay, it goes on for a while, but it gives you a good feel for it. So one of the things he worked on was the crashing of water, and this is a good one to represent. So the flow of fluids, different types of fluids, water, air, blood, it's difficult to analyze these because they flow in complicated ways. So how can you predict how water will move? Suppose you wanted to suppose you wanted to model how water flows and how it interacts with each other. How would you do that? How can you predict where water will go? Now this was one that Adam shared with me. This is probably about 3 years old. This is computer animated water. So let me show it to you again. It's not the latest technology. It's a little bit old. But for 3 years ago, it was pretty good. That looks pretty realistic to me. It's all computer animated. All right? And what they did, to solve these problems of flow of fluids, you do a math equation called Navier-Stokes. This is a famous problem in mathematics. And it's not known whether there exists a solution in 3 dimensions for this. Okay? And this is one of the $1 million Clay Math Institute's unsolved problems. Now, in case you didn't realize it, there were originally 7 unsolved math problems that if you solved one of these, you would get $1 million. Some of them have been solved. The Navier-Stokes one has not been solved. Okay? So anybody have Friday night? You've got Saturday, Sunday, the weekend. Work on this problem. You get $1 million. I only asked for 10%. Okay? So let me know if you get it. I'm sure I'll rebound in the news. But these are, of course, hard problems to solve, but really be significant problems in mathematics and in physics if you could solve these. These flow of water was used in lots of movies. Pirates of the Caribbean was one. If you use saw the Chronicle of Narnia, some of those, they used water. Anytime they were using the water, they're using it, representing it by using these types of approach of Navier-Stokes. Now, does that mean that that people in Hollywood have solved these problems, the Navier-Stokes equation, and they're just like, $1 million is not worth it to them? They're like, that's like 10 minutes of work time. No, what they do is they approximate it. And that's good enough for movies. They don't have to make it totally accurate. Because movies go fast enough, they can just, people will see it and they'll think, oh, that's realistic. Okay? So they approximate it.
After years in the classroom, math is going Hollywood, and it's making disaster flicks look even more catastrophic. From oceans flooding city streets to leaping, splashing sharks, these special effects show how the field of fluid dynamics is helping filmmakers use physics and mathematics to create more realistic animations in movies.
All right. Just really cool that this was in the news, talking about math and physics, making movies. Okay. Before we go to the next one, we have another T-shirt. So let's see. I'm gonna limit this to math majors at Central. So let's see. What could we say? Who is a math major who has taken the highest level, we'll say highest level math classes. I don't know what they are. How many people, who's a math major here at Central, math major, who's taken, what's an advanced class?
Real analysis and advanced class.
Okay, yeah, real analysis. How many have taken real analysis? Wow, that was really
There are
good.
any math majors here.
What's that?
First, you better ask if there are any math majors here.
Are there any math majors here?
Okay.
Are there anybody who would admit they're a math major?
Yeah, okay.
Okay, so real analysis sounds too far.
Probability theory.
Probability theory. We have
Raise your hand.
1, 2, 3. Yeah.
Best score.
Okay, we'll do it this way. Dominic, pick a number. On draft. 1, 2, or 3. No, facing me, but not them. Yeah. Okay, and you guys pick a number. Okay. So he picked 1. Just pick different one. What did you say? 2. Okay, and you pick 3, and the number was
2.
2. So you get a T-shirt. Okay, same T-shirt. All right. Actually, I like these T-shirts. We do this in the math department to kind of promote mathematics. I throw them out during. So I teach a large class of calculus. It's probably got more than twice as many people in here. And the occasional class, I'll throw them out. One time, we had we ordered some shirts in kind of the Texas orange, the Texas Longhorn orange color, and it came out wrong. It came out to be a bright orange, and it wasn't really a popular shirt. So then we came up with this idea: we'll do this for Halloween, and we'll give them away. Well, we sell them for like $5, and we'll say, "Where are your Halloween math T-shirts?" And it was great because I would teach class, and I could see like a whole bunch of students wearing these during class or on campus. You'd be walking around, you'd see a bright orange T-shirt there and a bright orange T-shirt over there. It was just really kind of cool. So we thought it was cool. Anyway, all right, simulating hair. Now, this is one of the first movies I remember. Not that I was alive in this thing. I remember watching this movie, and my daughters are really excited about the new Cinderella coming out. So that to me, that hair doesn't look realistic.
How could you?
What's that?
Like melted, I used to melted cheese.
Kind of. I think it kind of looks like Daffy Ducks.
Yes.
Okay. Not very realistic. Well, then there was Little Mermaid. And I remember Little Mermaid coming out, and that hair looks better, but still not very realistic. Monsters Inc. Okay, there, that looks better, but still not kind of like real hair, is it? I mean, it's you can tell it's kind of furry. There's a movie that came out called Brave. There's also about the same time a movie called Tangled. I could talk about either one, but I'll talk about Brave. How many people saw Brave? It wasn't that popular. Oh, okay, we've got maybe half the people here saw this. Okay, this is the story of a Scottish princess who is a very independent character, fiery character, perfect for my family. With some of my daughters, they really like the movie. I'm not sure if it's because they can relate or whatever. But how do you represent this hair? Now, one of the problems was what they wanted to simulate the hair so it looked wild and beautiful, but also stretches out when they run, but snaps back. One of the first attempts they did was, that didn't really kind of snap back in a realistic way. You move your head, hair doesn't really quite work like that. It's more like that. So how can you do this mathematically? Well, what they did, they used some differential equations, and the hair was simulated by a curve. They had some curve, and on the curve, then it was kind of like a necklace. They put a bunch of beads, and these beads could then move a little bit. And from each of the beads, they had springs. And some of these were related to cylinders of different sizes. And so you can kind of see a little bit here. They have these curves here, and then from these curves they started putting on the springs that came off of each of the sides to get something like that. All right. This was a piecewise linear curve. So they started out with just kind of a random curve here, and they smoothed it to something to look like that. And then they used the cylinders of varying lengths. So here's a little clip about some of this.
Marida's hair was seen as a character on its own, as an extension of what she is. Every single hair parameter was randomized slightly, so each hair has its unique way of moving and interacting with other hair.
And so now I'm going to show you, this is going to be a clip of a preview of the movie before it came out. Look at Merida's hair, the character's hair, and see, does that look realistic? And think about that in order to do this, they had to then use these curves that were kind of randomly generated. Then they had the necklace part with beads on it, and then the curls in the shapes of different cylinders of different sizes.
Brave, the new movie from Disney and Pixar presents Brave Stories.
Places, everyone. Oh, look at us there. Perfect family, perfect kingdom, perfect life. Now, let me tell you what things are really like around here. That's me, Merida. Mum tries taming my wild mauve hair, but I like it just how it is. And your parents are the king and queen.
No weapons on the table.
Oh, castle life can be restricting. Merida, stop! I need to live my own life. Follow my own path. I wished for things to change, and that's the problem. Seems I unleashed a wee tiny ancient curse. No, I'll do anything to make things right again and save the kingdom. You just have to be brave.
Coming to theaters soon.
Okay, so again, just really kind of cool. There's a lot of math behind it. You see the movie, you don't necessarily think about that, but they're using this math to make that movie possible. All right, let's see, another object that they simulated that was kind of recent was snow. Okay. So this, I remember growing up and watching this every Christmas. Rudolph the Red-Nosed Reindeer. Is there anybody who has not seen Rudolph? Wow, this is the most popular movie. Okay, what was the snow like? Flour, sugar.
Powder.
Okay, not very realistic. I know you guys don't have any snow here. we actually don't have very much in Utah either. We're kind of in the same weather thing as you guys are. 2 weeks ago I was in New York City, and it's always a little depressing when it's colder and more snow in New York City than there is in Utah. But, oh well. Okay, not very realistic. Then there was this movie, Ice Age. All right, better, but still not quite realistic. Okay, and then there was Frozen. Yes. Okay, very popular movie. What they wanted to do in Frozen was here was the task. Okay, this is kind of like Mission Impossible. Listen to me. Okay, and your task, if you choose to accept it, is to create an equation that would model snow so that if you change one of the variables, it will change the snow from crunchy snow to soft snow, powder snow to wet snow, to dry snow. It's just one equation. So that when they put it in, they can program it into some software so the animators can do this automatically. And of course, the movie takes place, in Norway, and so they want to, have all these different types of snow. Because, when you live like in Arizona, okay, there's like one type of snow, and that's like the snow on TV. That's the only snow you see. But if you live in areas where they have snow, I've lived in New Hampshire, where they have like icy snow, which is not very good for skiing. And then there's Utah and Colorado, which has powder snow, which is really nice for skiing. Okay, different types of snow. That was their goal. Can we animate snow in realistic ways to get all these different types? Can you do that? And make it move from one type to another very easily. Now, one of the techniques they used is iteration. Now, you may have seen some iterations before. Iteration is a process of applying a function repeatedly using the output to get the new input. So I'll take a math equation, f of x equals x plus 3, and I start with x equals 1. If I do that, if I put 1 in for x, I get 4. Now I'm going to substitute that output, which is 4, into f of x. So when I put it in there, I get 4 plus 3, and now I get an output of 7. This is the idea of iteration. If I take that 7, plug it in, I get 10. Okay, if I substitute that in, okay, the next answer is 15. You guys are really good. Okay, and I keep doing this process. Okay, in this example, it's kind of boring. Okay, but you can do this to produce complex behaviors, especially if you start with complex numbers or complex functions. Now, I don't know if complex analysis is taught here regularly. It's my area of research in mathematics. It's kind of what we call it's calculus with imaginary numbers. Now you have to be careful. I have to be careful when I say imaginary numbers because I was once talking to a neighbor who didn't have a lot of math background, and they were asking me, what type of math I do, and I said I work with imaginary numbers. And they looked at me a little bit weird, but then they came back and they said, could you help me balance my checkbook? And I was just thinking, it's not because of my imaginary numbers. So I could be a little careful. But it's calculus with imaginary numbers. Some of you may have seen fractals and Mandelbrot sets. Here's an example here's a video of the Mandelbrot set. And that's kind of the solution to this. What values here go off to infinity when I iterate that? So the black colors are things that don't go off to infinity. The non-black ones go off to infinity. The different colors represent how fast they go off to infinity. And with this very simple math equation, you zoom in on here, and you start seeing the same shape or very similar shapes over and over again. So just think, you're zooming in on this like you're looking out in space in a telescope, but you're actually, or looking in a microscope, a mathematical microscope. And if you do this, you notice you'll see the same shapes coming up over and over again, or similar shapes. It's just really interesting. You just start with a very simple math equation, you can get this. That's the idea behind fractals and Mandelbrot sets. That's the idea, and that is done through iteration. So in movie they used, for Frozen, they used some iteration. And they did they used the following kinds of math to solve this problem. And one of the other difficulties they had was, remember when we talked about Dash, you could put a grid on Dash. How do you put a grid on snow? Okay, it's not kind of connected there. So what they had to do was they used this idea here of taking the snow particles and in 3 dimensions, kind of looking at their shadow on the ground, and then applying the math equations on what we call mathematically a projection, do the calculations there, and then you get the new movements of the snow, and then you lift it back up. All right, and that's what happened here with what they did with that. Okay, and so with that they were able to do this, and so they developed this function, had these variables in it, these 4 variables, and if they raised these 2 variables, they got chunky snow. If they lowered it, they got powdery snow. If they raised this one, they got crunchy snow. They raised this, dry snow, wet snow. Okay, so now I'm going to show you a video clip, and then we'll talk kind of briefly. They'll say, here's an example of this type of snow because they've done this variable. And see if you can see the differences between the snow.
By varying our model's parameters, we can produce different types of snow. For instance, changing the snow strength parameters let us choose between powdery and chunky snow. On the other hand, changing these models varies between soft and crunchy snow. Finally, changing the hardening parameter varies between brittle and ductile behaviors.
Okay, now to get more realistic or more applicable, now I'll show you a video clip with them with some snowballs. And try to see the difference in the snowballs. Some of these will be wet snow. And then they'll also even show 2 snowballs being thrown at each other and what happens when they do this. Again, this is all computer animated.
We now illustrate our method on a variety of snowballs. First, we drop a snowball on the ground.
It's pretty good for snow, for animated snow.
We can also smash a snowball into the wall.
Yeah, I like this next one.
We can even make the snow stick to the wall. More impressively, our method can also handle snowballs hitting each other.
Pretty cool, I think. So, next time you see Frozen, think about that. How they had to use all this background to make the snow so they could actually make the movie. Really kind of interesting. Okay. Who has the birthday coming up? Who has a birthday, let's say within 5 days? Okay. I guess you win. When's your birthday?
Tomorrow.
Tomorrow.
That's not official birthday though.
Okay, you get a t-shirt here.
Oh, yay.
I can get it to you. All right. Good. All right. So, in conclusion, I'm going to end up here. Next time you go see a movie, what should you do? Well, first of all, enjoy the movie. Hopefully it's a good movie. Okay? Think about how did math help make this movie? So it may not be the first time. When I saw Frozen the first time, I didn't think about the math. But then afterwards, I started thinking, okay, how could they do some of this stuff? How do you actually make it possible to do this? But even more importantly, think about how can you make something better with math? How can you improve the world? How can you solve some of the world's problems using math ideas, math techniques? That's the message again I want to get across to you. Okay, math is a big, wide open area. It can help in solving lots of problems today. Problems with Ebola, problems with world hunger, problems transportation problems, pollution problems. It would be great if people here, some of the students here, were able to solve some of those problems. And I'm almost certain to solve those problems, you're going to have to use some math. So do that. I want to hear about this. People from Central Washington solving these problems. Thank you very much.